the percentages?
60% nitrogen.
60%? 60% is a little off. Yeah. Let's look at the air composition. Well, if we look at the air composition, it says, what? 78% nitrogen. Well, usually I just round it. You know, I round this to from 80% nitrogen, and I round this to 20% oxygen, because it's just easy numbers to remember. If you want to be more precise, that would be better. But an easy thing is that air consists of, the composition of air consists of 80% nitrogen, 20% oxygen. Now, these compositions aren't totally fixed, because it depends on elevation and location. But, this is just the average composition of dry air. Is this dry air? I'm pretty sure it's dry air. Now, what does that mean? Does that mean if I have 100 grams, do I have 80 grams of nitrogen? Yeah. If I had 100 grams of air, do I have 80 grams of nitrogen? And in other words, let's just take a 100 gram sample. If I have 100 grams of air, then that would mean I have 80 grams of nitrogen and 20 grams of oxygen. Is that correct? Normally, yeah, that would be correct. But for gases, we don't usually do a weight percent or a mass percent. For gases, we typically do a molecule or mole percent. And so this is actually wrong. These percentages are percentages by moles. Mole percent or molecule percent would be like this. If I had 100 moles of air, how many moles of nitrogen would I have? I'd have 80 moles of nitrogen and 20 moles of oxygen. Mole is just accounting like a dozen. If I had a dozen, if I had a dozen or 100 dozen, if I had 100 dozen air molecules, I'd have 80 dozen nitrogen and 20 dozen oxygen molecules. Or I could say for every 100 molecules, now mole of molecules is a lot more than a molecule. But for every 100 molecules, I'd have 80 molecules of nitrogen and 20 molecules of oxygen. Now, from the ideal gas law, the moles will be proportional to what? So when we look at the ideal gas law, we note that N is equal to PV over RT. So the number of moles is directly proportional to the pressure, and the number of moles is directly proportional to the volume. Yeah. And so this gives us two additional laws here. The first law we're going to call Dalton's law. This is what Dalton's law says. Dalton's law says if I have 100 atmospheres of air, how many atmospheres of nitrogen do I have? I would have 80 atmospheres of nitrogen and 20 atmospheres of oxygen. That's because moles and pressure are directly proportional to one another. Whereas moles and mass aren't. You know, the proportionality for moles and mass is going to depend on how much the molecule weighs. So nitrogen molecules weigh a different amount than oxygen molecules. And so we need to know what the molecule is. But over here, we don't need to know what the molecule is. We just have that. So this is Dalton's. Or more typically, we don't usually work with 100 atmospheres. What's normal pressure? Roughly, normal day-to-day pressure. Well, normal day-to-day pressure is 1 atmosphere. So if I have 1 atmosphere of air, how many atmospheres of nitrogen do I have? 0.8. And 0.2. We'll just go with 1.0 atmospheres there. The decimal place is correct. That's Dalton's law. So Dalton's law says this: if you add up the pressure of the oxygen plus the pressure of the nitrogen, we get the pressure of air. And so let's say if I had, this is nitrogen. If I had 20 atmospheres of nitrogen and 80 atmospheres of, or no, I got it backwards. If I have 80 atmospheres of nitrogen and 20 atmospheres of oxygen, what is the total pressure of the air? 100. Yeah, so 20 atmospheres plus 80 atmospheres gives us 100 atmospheres. And so what Dalton's law of partial pressure says is that the total pressure is equal to the sum of the individual or the partial pressures. So we just add up all the gases. This makes sense because if I look at a container, let's say this container contains nitrogen and oxygen. The nitrogens are going to generate 0.8 atmospheres worth of collisions with the wall. So there's going to be collisions with the wall generating pressure. The oxygens are going to generate the other. And so 80% of the collisions are generated by the nitrogen, 20% of the collisions are generated by the oxygen. And so if we want to see what the total number of collisions are going to dictate the total pressure. So that's going to be this is Dalton's law. We have one more law called Avogadro's law. Well, Avogadro's law says this: if I have 100 liters of air, how many liters of nitrogen do I have? Turns out, yeah, I'd have 80 liters of nitrogen. And how many liters of oxygen would I have? 20. And so what Avogadro's law says is that 20 liters of oxygen plus 80 liters of nitrogen gives us 100 liters of air. And so Dalton's law we can sum up. P total is equal to P1 plus P2 plus however many gases we have in there. So we call that the sum of the partial pressures. Equals the sum of the partial pressures. So the total pressure here is equal to the sum of the partial pressures. What Avogadro's law says is that the total volume is equal to the sum of the partial volumes. So we just take the individual volumes and add them up. Both of these cannot be true simultaneously. So if I look at this, we have these. We have the mole percent. Let's go with the mole percent of 80% nitrogen. That's our mole percent. The mole percent gives us a mole fraction. The mole fraction is going to be 80 out of 100 will be nitrogen. So 80 moles of nitrogen per 100 moles of air. That's called the mole fraction. These are always true. However, the pressure fraction is going to look like this. Atmospheres of nitrogen for every 100 atmospheres of air. It's a pressure fraction. So this 80% is 80 out of 100 moles, or 80 out of 100 atmospheres. But when we do this, we have to place a restriction. And the restriction we place here is what we call constant volume. At constant volume. There's no restriction on the mole fraction or the mole percent. There is a restriction on the pressure fraction. The other thing we look at is the volume fraction. Volume fraction will be 80 liters of nitrogen for every 100 liters of air. But there's a restriction on this one, and this one has to be at constant pressure. So we can't have both constant volume and constant pressure simultaneously. It has to be one or the other for this. One or the other. But not both together. So let's break down a container of air in terms of Daltons, in terms of Avogadros. So I'm going to take 100 liters of air. Like this. And this 100 liters of air will be at 1.0 atm. Now, this 100 liters of air consists of nitrogen and oxygen. Mostly nitrogen. of oxygen. 20% of the molecules are going to be oxygen molecules, 80% will be nitrogen molecules. Now what we're going to do is we're going to separate the oxygen from the nitrogen. And there are two ways to do this. One way is like this. I can do this at constant volume. What that means is this. If I separate out the nitrogen from the oxygen, how many liters of nitrogen will I end up with? I'm going to remove the nitrogen out of there. And when I do that, I end up with 100 liters of nitrogen. But this 100 liters of nitrogen will not have any oxygen present. This nitrogen. So all of a sudden 20% of the molecules are missing. Where are those? Well, those are in another container here. How many liters of oxygen do I have? I'm going to have 100 liters of oxygen. And so how can I have 100 liters of both oxygen and nitrogen? Because I only have 100 liters of air. And so this is a situation where 100 liters plus 100 liters gives us how many liters? 100 plus 100 equals 200? No. 100 plus 100 equals 100. Now how could that be? How could 100 plus 100 equal 100? Well, what we're going to do is we're just going to combine these two gases into one box. And when we do that, then we put both the nitrogen, which are the black, and the oxygens, which are the orange, in the single 100 liter box. And so what this means is that the volume doesn't change. You know, the volume of air is equal to the volume of nitrogen, which is equal to the volume of oxygen. But what's different? Well, this first volume here is going to be missing 20% of the molecules, which are oxygen. If it's missing 20% of the molecules, there are going to be fewer collisions. And so the pressure here is this. You know, this is 1.0 atmospheres of air, but do I have 1.0 atmospheres of nitrogen? Am I getting the same number of collisions? No, I'm not getting the same number of collisions because the oxygens are missing. So what do you think the pressure is here in this container? It's 0.8 atmospheres. I only have 80% of the molecules left in there. Well, what happened to the other 20%? They're in this box. But this box has 80% of the molecules missing, and it only has 20% of the molecules there, so it's 0.2 atmospheres of oxygen. And so 0.8 atmospheres of nitrogen plus 0.2 atmospheres of oxygen equals 1 atmosphere of air. And so this is Dalton's. Dalton says we just add up the pressures like this. Alternatively, I could look at it from Avogadro's perspective, the same exact mixture. So I'll just bring it down here. This is going to be at constant pressure. So what I want to do is I want to maintain constant pressure. And so what that means is I want to make sure I end up with, well, I have 1.0 atmospheres of air. I need to end up at 1.0 atmospheres of nitrogen. How can I get 1.0 atmospheres of nitrogen? Well, I have to make sure that the number of collisions doesn't change per unit area. Well, if nitrogen only comprises 80% of the molecules present, then what I need to do is I need to shrink this box to 80% original. And so if this box is 80% of the original are 20% smaller, then I'll get the same number of collisions I had with the oxygens present over there. I'm compressing it down a little bit, so this is going to be 0.8 liters. Well, 0.8 liters of nitrogen. Well, how much oxygen will I have? Well, I know I need to have 1.00 atmospheres of oxygen. And so what I have to do is, if I get rid of all the nitrogen, I'm going to have to squeeze the container down to much smaller size. So I get this more concentrated so that the number of collisions is the same. So the number of collisions here is the same as the number of collisions here per unit time, which is the same as the number of collisions there. And the size of this container is going to be 0.2 liters. And so if I take 0.8 liters of nitrogen plus 0.2 liters of oxygen, how many liters of air do I get? 1 liter. But if I take 1 atmosphere of nitrogen plus 1 atmosphere of oxygen, how many atmospheres am I going to get? 1 atmosphere. Exactly. That's good. And so the pressure is constant here. That's because of how we add the box. We aren't getting rid of any boxes. We're just putting these two boxes together. When I put those two boxes together, I get 1 liter. And pressure remains the same. Right. Any questions on this so far? No? Okay, let's take a break now, and then we'll start up again after the break.